Hi, I'm David Greenberg at Helmholtz-Zentrum Gestalt. Welcome to another episode of ML at HZG. We have a very cool paper. Hi, I'm David Greenberg at Helmholtz-Zentrum Gestalt. Welcome to another episode of ML at HZG. We have very interesting tools to accomplish it. So coming at this from the earth science perspective, a lot of the data sets that we deal with in atmospheric science, ocean science, other related fields have temporal and spatial structures. So there can be sort of thought of as videos, although often as videos with many, many more channels than a typical video. So neural networks which can generate these, which can take them as inputs, which can generate them as outputs are really interesting here. And that's part of what attracts us to this particular paper. They are applying these networks for two specific tasks, which we're going to get into. The paper is going to be presented by Tobias Machnitzki, a new PhD student in our group. I guess, Toby, you'll introduce yourself a bit and
right now,
and go over it, over the material, over the tasks that we're trying to solve, and how it's done. So I will hand over to you now.
Yeah, thank you, David. Like David said, I'm Tobias. I just started last month at David's group as a PhD student in machine learning. And I'm coming from a meteorological background. I made my master's in meteorology in Hamburg. So yeah, I'm learning a lot about machine learning at the moment. And so I'd like to invite you on my journey through this paper, which is about GANs, generative adversarial networks. And at the beginning, I'd like to have a little recap on what actually is a GAN. I think we talked about GANs in episode 13 or something, or?
Yes, at episode 5 for the first time, where they were generating images of clouds from meteorological fields. And then again in episode, I think 13, yes, where they generated high resolution images from low resolution images.
Right, something like this we're going to do today as well, generating high resolution images. This is called video super resolution in these kind of tasks. And yeah, so what is a GAN again? A GAN is actually, or in most cases, a GAN is a neural network consisting of actually two networks. We have a generator network and a discriminator network. The generator network tries, as the name says, from something like random noise, generate images or anything else. In this example, it is images. And the discriminator gets either a generated image from the generator or something from the real data distribution and tries to tell if it's a real image or if it is a fake image. Right. You can a little bit think of it as a game. Either of one is trying to win the game. So each is trying to get better than the other one to be better. The generator always tries to fool the discriminator here.
And this is the criminal and the smooth criminal, huh?
Yeah,
right. Title. So it's the generator is sort of trying. I like to think of it as counterfeit money or fake goods of some kind. It's making a fake copy.
Fake images.
Fake images, yes.
You know these painters who try to fake the Mona Lisa.
Oh yeah.
And they get better and better. And the discriminator is something like the police, and they try to tell apart if this is now a real image or if it's a fake image.
Mm-hmm.
So yeah. And only if the discriminator gets better, the generator can get better. Because if the discriminator doesn't accomplish its task to tell if it's a real or fake image, it can't tell the generator if it's doing a good job.
So you're saying they both improve by having a good opponent.
Right.
Okay.
So that was general GAN, generative adversarial network. So now we're going to talk a little bit. What does the TECOGAN, and the TECOGAN is the paper, is the network which they built in the paper, Learning Temporal Coherence via Self-Supervision for GAN-based video generation, which is the paper we are talking about. What are they doing different than compared to normal GANs? And they propose they are doing 3 new things. First is they apply some recurrent generator. That's not something they invented. They used this from other papers, but I haven't seen this very often yet. So the second thing is they use the spatio-temporal discriminator. So that's something very new, which they invented. And then new proposed laws, the Ping-Pong laws. And we'll go over this one by one and try to get into this stuff and find out and figure out what each of them is. So here we have at the top, this one is just another image of a very normal GAN. We have the generator and we have the discriminator part. The generator gets some sort of sample. So in this example, it's conditional GAN, because we don't only throw noise in it, and we might not even throw noise at all in it, but we have some conditional input called AT, and it's trying to convert this into some other distribution, GT. The discriminator gets either an image from the generated distribution or from the original distribution, which the generator is trying to learn, and tells apart if it's now a fake sample or a real sample. So what are they doing different? Let's have a look at their new proposed, or not their proposed generator, but the frame recurrent generator. The frame recurrent generator reuses prediction it already has made. So it still gets the input as before, the input AT. And if we're talking about a video super resolution task, so a task where we are trying to predict high resolution images from low level resolution images, this AT might be some low resolution image. And what we would like to get is some predicted high resolution image. But to get there, we can do some recurrency and use the predicted image from the time step before to enhance the actual prediction. And we are doing this by estimating some flow, some field of motion, some optical flow, which then can be used to forward the last predicted image to the timestamp as our low resolution input.
So I think I'm following this description of how these networks work, but can we just jump back? I'm getting a little bit lost. What is the overall task we're trying to solve here? I think this is a super resolution task.
Right.
But it's for videos.
Right.
So what are the overall inputs and outputs in this task?
The overall inputs, so that's a very good question, right? I didn't really tell that. Because we are doing video super resolution, which is way different from just single image super resolution, we have to think that our outputs have to be smooth. And smooth means they have to be coherent in the spatial dimension as well as in the temporal dimension.
Okay, so we want our network to take in a low resolution video,
right,
and then it outputs a high resolution version of that video.
Right.
Just like we were trying to do that for meteorological fields, but for single images in episode 13. And we want to do it for whole videos.
Exactly.
And you said one of the difficult aspects of this is smoothness. What is smoothness here?
Smoothness doesn't really come in here yet. Therefore, we don't know yet why we will soon need this motion compensation part. But if you would like, if you are just using single inputs and try to predict from single input one by one a video sequence, you probably will get a lot of very sharp images, but they might not be temporal coherent, which means you might have some flickering in the images or something like this. And since this is not visually appearing to a human person, we would like to restrict the generator in just smoothing the output along the temporal dimension. Okay. Right? And this recurrent generator helps with this because it will rely on what it has predicted on the step before, so that the next prediction can't be totally different from the last prediction. Okay. So we might later talk a little bit more about this motion compensation, because it's actually a very huge thing in this network, which is not yet here really explained. So this is a whole neural network for itself, doing some kind of flow estimation and some, I would call it transformation from the flow estimation to get the predicted high resolution image from the previous prediction to match the time of the actual low resolution image. So I think that's basically the generator part of it for now, because we're going to have a deeper look at the motion.
So it's using each frame of the video output by our generator, output by this neural network, depends on the low resolution frame it's trying to increase the resolution of, as well as the previous high resolution frame itself that it itself had output,
right?
But which has been moved around or distorted to compensate for motion across the image.
Right. That's it.
Okay.
So the next thing we will talk about is the discriminator, the other part of each generative adversarial network. The discriminator usually gets either a real sample or a fake sample. And in the case of these, of this temporal, I'm missing the word, the spatio-temporal discriminator, we concatenate multiple frames that the generator predicted and give them to the discriminator at once. And we're not only giving him the predicted images, but also the ones with the flow correction to match the target time point. So I tried to figure that out a little bit more here, what all of this means. So the target prediction is GT. And since our generator can predict sequences of arbitrary lengths, we can just have it predicted GT+1 and GT-1 and all of them together. So that's where we get all of them from. And now what we have, the other triplet, which is getting also, is as well in the middle the GT, so that's the same. But as well, we use the prediction, which we have here, use our warping, which we've seen before, warp it to the time point of our GT. And we do the same for the +1 prediction. So that in the very best case, we have 3 times at the lower bottom here, we have the same image, right? Was that understandable? Okay.
We're having a bit of audio feedback from somewhere. What is happening here?
Yeah, I don't know.
Everyone should be muted in this room, except me.
Maybe it gets better soon, yeah.
All right, let's keep trying.
Right. So what the discriminator actually gets is they just stack this information along the channel the channel dimension. And then the discriminator gets all of these information simultaneously. So that's what they call the spatial temporal discriminator. And they state that it's not something new that you give multiple images to the discriminator. So this top row part here, that's not something new. But I think what's new is that you provide the flow compensated bottom row to tell the or to help the discriminator tell the differences. So you don't even give it only the flow estimation, but already the warped images.
So can you give us some intuitions about why we'd want to provide multiple images and why we'd want to warp them when we provide this to the discriminator?
Okay, so when we're talking about multiple images, we're talking about the top row here first. So providing multiple images simultaneously to the discriminator will help the discriminator to tell kind of the smoothness of the images. So it will work, it will look once at a sequence of real images from a video, and real images in a video, there won't be any flickering in the here. If it's a normal video, you won't see any flickering between the images or something like this.
If we see the real data.
If we see the real data, yeah.
Okay.
So if we see now the fake data, and there will be any flickering in it, the discriminator will have it very easy to tell real data apart from the fake data. And therefore, we would like to have a sequence of images, because in a single image, you might not see any flickering or any other artifacts, because single images might still look sharp and good, but then the video again might not.
Right. Okay. So this explains why we want to look at more than one image at a time.
Right.
Why do we want to warp them? Why do we want to warp them to correct for, motions across the frame?
Right. And this is just an additional help to help the discriminator to provide better loss for the generator, so that the generator can produce higher resolution, or not higher resolution, images with more detail. Because in the best case, we have 3 times the same image with the same detail, which in practical will never occur. But the closer they are, the better the predictions are, right?
Mm-hmm. Like for me, the way I mean, the concept I have of this, which may be just wrong, like the way I explain this to myself is, the pixels change for multiple reasons. They change because things move around, like the camera moves or objects in the frame move, and they move because of actual, say, physical changes, right? Like, if I'm taking a picture of a light bulb, the light bulb can turn on and off, or I can move the camera, or the bulb can move. And if you estimate, it's somehow much easier to maybe estimate motion than it is to estimate other kinds of changes, the way that shadows change, the perspective changes from the camera, lens flare. But so if we can estimate motion separately, then the remaining task becomes kind of more focused for the generator and the discriminator, I guess. This is my intuition. I don't know if
I would see it the same way. You separate both tasks.
Mm-hmm.
Right.
And we haven't talked about how the motion is estimated. I don't know, we'll get to that later, huh?
Yeah, I think we get to it right now.
Okay.
So that's the basic equation of optical flow for warping. And so this is more the analytical approach. So the idea is, if we imagine a grayscale image, we can tell the intensity of each pixel, X and Y, and if it's a video, we have the time dimension as well. Well, I didn't want to show you this yet. The time dimension as well. So we can...
We have a question, I guess this is about to be answered from the chat. What does warped mean?
Yeah, we'll come to this right now.
Yeah.
So we can describe the properties of each pixel with the intensity right here. And if we now say for infinitesimal changes, we can just add like dx, dy, and dt, and do some Taylor expansion and divide by dt. We get this equation. And this equation gives us a vector for each pixel and each point in time. And this vector now can be used to tell some kind of flow field. It's a 2-dimensional field. So where does each pixel move in form of intensity? And this looks a little bit like this, or we can visualize it as this. If we have a static background, so this is a video of 3 people walking in different directions, but it's a static camera, so the background doesn't change. If we now calculate the optical flow of this image, we can see that there is no flow for the background because it doesn't change, at least it shouldn't change. But the people are walking in different directions. So we get some flow estimations here. So this would be more the analytical approach, but it's very slow and not that good in reality. Therefore, we used in the TECOGAN paper and in general now for these kind of tasks, we used full neural networks. So the warping actually is using some kind of flow estimation field like this, optical flow field, and then there's some transformation from the original image using the flow field to get the next frame.
So you're saying that there's a neural network which is different from the discriminator and the generator. It's a new network.
It's completely new, yeah.
And it's taking the video and estimating the flow between each pair of successive frames.
Right.
And that flow itself is a function of space. So it's a vector field saying
Right.
how things are moving around. And I guess we're seeing it in this color plot. You have these 3 different people. I guess the RGB, this is some kind of representation of velocities in color space.
Right.
I can't help but notice, I'm sure some of the other people listening will think this as well, that how similar this looks to the continuity equations we see in fluid dynamics and earth science. You have the first two terms are advection, and then the third is kind of in place physics. Well, actually, in fact, it is a conservation law. So then this is like the something related to like an incompressible fluid or something like that. I don't know. Maybe I'm getting it a little bit wrong.
No, it's okay.
But that's exactly what you want to have, right? It's an advection of the pixels into the next frame, into the next time step.
Right.
But this equation would be valid only if there are no changes in the total illumination of,
Right.
of the picture.
Right, Mike.
So there are
the
a
amount
lot
of
of
light is
assumptions
increasing,
going in
yeah.
there, yeah. We have some more problems as well. What are we going to do at the corners? Because unlike on the Earth, we don't have circular boundary conditions. So we have a problem here. And in the TECOGAN, they circumvent this problem by only using the center of the flow estimation fields, so that you always have enough space to calculate all your flow. Right? If you crop just the center.
They only use it for training, but I mean, they generate an output the size of the full input image when they actually use the TECOGANs after training them, right?
Yes.
But for training, they kind of compute the objective function just using a center region.
Yeah, if we go back, we can see this. Because we're talking about this input here right now.
Mm-hmm.
And they stack the low resolution input, if we're talking about video super resolution, they stack it together with the warped image. But the warped image already has a way higher resolution, right? So they can just use the center of the warped image and stack it along the low resolution image, I think.
Okay. Okay.
At least that's how I understood it in the paper, yeah.
Oh, well, let's
It
keep
might
going.
be,
We can worry about those technical details later if there's time, yeah.
Yeah, so that's how you estimate the flow. And then the warping itself is just some transformation. It's not something magical like a neural network or, yeah.
So we're saying basically, given the vector fields estimated by our flow estimation network, we can then use those fields to transform every image by locally moving pixels around.
Right. So if we're done with the laws,
yeah,
with the warping.
Before we move on, maybe can we just zoom back out to the original GAN slide just to refresh everyone? I think that would be really useful. Yeah.
This one?
So then, can we just restate the problem and then what's being done with all the stuff you just covered in mind? We're trying to go from low res to high res videos.
Right. We have our low resolution input here. And we're using our frame recurrent generator to output a high resolution image. And this we do not only output a single image because we're doing video super resolution. The input are multiple images, the output are multiple images as well. And the discriminator then gets multiple images as well to help the generator to output sharper videos, which are coherent over time. That's what we're doing. And everything we covered in between now was just going into more detail about the warping here. And we use the warping again for the discriminator part here, right? And we talked about that. So we are using the low resolution images to estimate the flow field. And then we can use our, where is it? Then we can use our prediction we made and the prediction before to try to warp our prediction before to the one that we just made and match them.
Right.
So that's what we've been talking about so far. But all this sounds really good so far. So why didn't they just give up here? That's a good question, right? Well, there is some problem with the generator. Even though that's a very nice structure to use, it has one problem, because once the generator makes one wrong prediction here and does something wrong, maybe introduces some kind of black square, then the black square will be here as well, because it will be just warped with the flow and will be used again in the frame recurrent generator. So the black square might accumulate, or we get like a whole black image or something like this. And now we have to think about how can we constrain the generator from doing this? How can we constrain it from reusing wrongly made predictions? And they tackle this by introducing some new laws they call the Ping-Pong laws. And the Ping-Pong laws is actually something that's kind of intuitive, I think, at least to me, because what they do is they are not using the video only in the forward direction, but as well in the backward direction. So say you have a video with an image sequence of 10 images. You can use the sequence once forward to go from 0 to 10, and then backwards. It's just like, imagine a car driving forwards in the image once, and then if you play it backwards, it just drives backward. And in the original data, if you subtract these images or calculate any kind of loss or norm on them, they should be the same, right? So if you subtract them, there should be 0. So if you do the same for the predictions, you generate once from the forward flow and once from the backward flow. And if you then calculate some kind of loss between them, it should, in the best case, be 0 for each frame separately.
So you're taking a little segment of video and you're basically saying, let's play it forward and then backward.
Right.
So we have like, you know, whatever, a ball falling down and then going back up, you know,
Right.
an egg breaking and then coming back together, something like that. And then we're saying, given this video which plays forward and then in reverse, if we put it into our network, get a high resolution version, it should also exactly go forward and then in reverse.
Right, exactly like that.
Okay.
And they're using some kind of norm, like a very standard L2 norm here. I think we covered this in several videos before. So they just sum up all the least squares between them. And this is, has actually even some kind of intuition to it, because the short-term accumulation of wrong predictions will be constrained here in this part, right? Because this is where the turning point is. So with the ball falling down and going back up again, let's just imagine that the frame N is where the ball hits the ground. If it makes some mistake here, then it can only accumulate to up to this frame, because we're already measuring the distance between these two frames. As well as if it makes something wrong at the very beginning, it will be evaluated at the very end. So this is some kind of long-term restriction. So we have some long-term consistency. And because we can make this ping-pong laws, these lengths here, of arbitrary lengths, we can even have arbitrary lengths output of the generator and restrict them from beginning to end, so that no artifacts can accumulate. So I think that's a very clever thing to do here for this recurrent generator to.
Yeah, it's a very clever trick. I have to admit, it hurt my brain quite a lot when I read it the first time. On some intuitive level, it should be impossible, right? Because, you know, you're trying to predict a video into the future and then into the past with the same network. So my first intuition is it's completely impossible that, you know, the arrow of time flows in one direction. If you learn to predict in a way which entropy increases, you're not gonna be able to go backward. And of course, you know, your video could be anything. It doesn't have to obey the laws of physics or thermodynamics, but still it does have certain trends and you have to reverse it. But then I think what makes it a little more sensible is that even though you may have to sometimes reverse the arrow of time, you do have always the low resolution information to guide you. So if, in this case, when you're evaluating the ping-pong laws, yes, you have to go backwards in time instead of forward, starting at GN, starting at where the ball bounces, but you have this low resolution information which is doing the same thing. So maybe this makes it a little more possible. it still really hurts my brain to think about this, why this is possible.
I think you can't think about it as a physical problem, more like from the image perspective itself, right? Because we're not talking about flows like in the atmosphere here.
True, but the video still has some statistics, and those statistics will have some trends in the forward direction of time, and they may not have the same statistical trends in the backward direction of time. But I mean, I guess it still works. Clearly it works. I have these great results, which I guess we'll get to at some point.
Yeah, definitely. We will talk now a little bit more about the losses, and this is a more mathematical part now, but we get through it each part, and at the end it will all make sense. It's not really a lot. So we start with the discriminator. We have the discriminator loss, which is kind of a standard discriminator loss. I think it's just the cross entropy loss, right?
Yep.
And so that's what we use for the discriminator. So I think we are done with that. The interesting part is the generator. Because
so can I just, so D is the probability the discriminator thinks something is real, yeah?
Right.
And it's trying to minimize this. So basically, I'm sorry, it's a negative X. So, okay, for B is which is the real data, which is the fake data? Oh, the B is the real data.
Right.
And so it wants to minimize negative log D. Right, so basically it wants to minimize, so D should be the probability it's fake then, huh? Because it's trying to minimize negative log of D, which means maximize log of T. No, okay, D is the probability it's real, yes. Sorry, I'm just confusing everyone needlessly.
Yeah.
But D is the probability that it's real. So D is between 0 and 1. And for the real data, it wants to be sure that it's real as best it can. For the fake data, it wants to be sure it's fake, so it wants 1 minus D to be big.
Yeah.
Okay, cool.
Maybe we should go back here one step and again show what is IG and what is IB. And I think IG is just generated triplets, and IB is the target triplets, and they call all of this IB, so at the top B, and this IG. So if we go back to the loss, everyone knows what we're talking about. Here are these ones. And ST probably stands for temporal and structural.
Spatial.
Or spatial,
yeah.
sorry. Yeah, probably. Okay, so that's more standard thing to do in general neural networks for any kind of classification task. The interesting part is the GAN loss. So the one for the generator. Because the generator loss is...
a little complicated?
Yeah, it's just the sum of many different losses. So if you look at it like this, it's complicated, but if you look at the losses each by themselves, we get through it.
This has been a trend in every GAN paper we've seen. The GANs were originally this very simple formulation, right? The generator fools the discriminator tells real from fake data. But
this
every time
only this adversarial loss.
Exactly. That would be only the adversarial loss. But every time we've seen a GAN, whether it was for the real fake clouds episode or the big picture episode, there were always these extra loss terms where the discriminator has to detect real from fake. Okay, easy. The generator has all these other jobs that are represented by these other loss terms, and it has to minimize the sum of losses.
I mean, we're talking about a C-GAN, so conditional GAN, so we need some additional loss anyway.
You don't have to have no, you can basically just provide the conditioning inputs. In this case, it'd be the low resolution sequence. You can provide that to the discriminator and the generator, and then that's pretty much it. I think when we looked at the PIX-to-PIX framework by Isola et al. In real fake clouds, and I think it showed up in, I think it may have showed up in big picture as well, but they looked at, I mean, they have all the extra loss terms, but they did try it with only the GAN thing. I think it becomes a little too imaginative and begins to do its image translation task and come up with all kinds of fanciful outputs which don't really match reality at all. But you don't necessarily mathematically have to have it just because you have conditioning. In practice, it seems you do need it. Yeah. But so you have a ton of these terms. So what are they and what are we doing here?
Maybe we start not in the right order because we were talking already about the adversarial laws. So the adversarial laws here, that's what the discriminator outputs. So that's what the discriminator outputs. So it's the probability that the image that generator produced, or the videos that the generator produced, is real. So
it wants to fool the discriminator.
Right. So we want this. Yeah. This is to fool the discriminator. Then we have a content loss, which is just an L2 loss. So
sum of square errors, like regression. Yeah.
We don't want to have this too big. We can control all these parts by adjusting the lambda parameters. So if we just have a very large content loss, the output would be very smooth. And many different papers showed these before using only content losses. And that's the whole point in many cases of using adversarial networks, generative adversarial networks, to get higher details in your outputs, right?
So just refresh our memory. So the content loss is on the bottom.
Right.
Remind us what G and B are.
G is the prediction and B is the original video.
So B is the target, the high resolution video we were trying to generate, the training data, and G is the output of the GAN.
Right, and we're doing some pixel-wise comparison between them.
Okay.
Frame by frame, and in best case they are equal, and this will be 0, sure. And going further, we might now have a look at the ping-pong loss, which we just had a look at, right? The ping-pong loss was just this. So if we write this out, it's not very different from an L2 loss, like we said before, because but we're taking the L2 norm over the prediction in forward and backward direction. So that's what we covered just before. This should be 0 as well, like all the losses. I don't even need to state that again. Then we have the perceptual loss here. This loss, L phi, we were just talking about this before. Maybe you want to say something about it.
Yeah, I mean, we saw this in some previous examples as well. We definitely saw it in episode 5, maybe episode 13 too. But the idea is phi would represent something like some neural network. I think you can use the discriminator itself, but you could also use an image classifier trained on some standard available data set where it's learning the difference between a dog and a cat and an airplane and whatever, right? So it has all these neural network layers, and every one of them has activations which turn on or off to a certain level when you give it an input. And the idea here is if we take the two videos, right, the true high resolution target we're using to train our network, and the network's best guess of high resolution from the low resolution video, we can put them both into these classifiers, discriminators. We can put them both into this existing neural network and say the activations of all the units and all the layers should be more or less the same. And what I'm seeing here is that it's taking the basically the activation vectors. If you think of all the activations of all the units.
Yeah, that's basically the cosine loss, right?
Right, the cosine of the angle. Yeah. So basically it's saying that if they're equal or if they're a multiple of each other, then that's good. So we want basically kind of the same activations of these features, which is to say, you could start off like the content is just saying, okay, look at the raw outputs and they should match. And then here we're saying, not the raw outputs, but rather these complicated nonlinear transformation of those outputs in terms of which features are useful for image classification, which features are interesting to a neural network that's performing a task. Those features
like
should
the
match.
Activation maps where the edges are found, where the colors are found.
Yeah,
stuff like
whatever is useful for learning that task. And I guess you start to see more complicated features like edge detectors and orientation selectivity when you get deeper in these networks. But so it's saying we're using pre-trained networks as kind of feature representation. It's saying the features represented by these networks in their hidden units and their deeper layers should be the same for the high resolution video we're trying to produce and our current estimate of it. So we're saying we should produce the same features.
Right. So this is some sort of loss which more represents like the human perception, if I correctly understood that.
Yeah, so there's ways of
the
calibrating
intent.
this.
Yeah.
I'm not sure if they used it for this task, but they use it for evaluating the results. But that basically, if you look at these features, so you have a pre-trained neural network, say classification, is identifying image classes from images, right? So it generates all these nonlinear activations. One thing I think that they talk about, and one of the references talks about, is if you ask humans to tell you how similar two images are, their decisions to find some kind of implicit metric of distance between image pairs, and it's possible to kind of mimic those metrics pretty closely using linear functions of these activations. Right. So this is one way of estimating how far two images or videos are apart according to human perception.
Right. So we now covered all this later part of the GAN loss. Now we can go a little bit to the warp loss here, because the warp loss is only intended, as far as I understood, to restrict the flow estimation network, because this is trained directly with the generative adversarial network, so it's trained inside. And to actually train it, sure, it needs to be restricted in some way. And it's just another kind of L2 loss here inside. And we just calculate the L2 loss from the input, from the low resolution input, and the warped low resolution input, from the previous low resolution input to the input. So from t-1, we warp to AT, and if the flow estimation network F is doing a really good job, AT will be the same as the warped image from AT-1 to AT, right? And then this will be 0 as well. Mm-hmm. And this restricts the network F, which here is the flow estimation network.
And the flow estimation network is trained at the same time as a generator and discriminator, huh?
Right.
This is quite ambitious, training 3 networks enough in case 2 networks was too easy, huh?
Well, yeah, it's not like you're training them simultaneously. You always train them step by step, right? You have one update step in the discriminator and one update step in the generator. And the warping and the flow estimation is part of the generator. So yes, it's big network. Mm. But you don't have to train the discriminator at the same time. You usually do this alternating, step by step. Do we have maybe any questions to this?
No, not yet, but this is a great time if anyone wants to ask in the Zoom chat. Marcel, I don't know if anyone's asked in the YouTube chat. The YouTube viewers are real lurkers. Come on, guys.
Right. Okay, maybe let's have a look at some results now, right? We talked about all these kind of theories and stuff, and they provide such nice results with the networks. I mean, we're talking about that this all works, and we want to show now, we talked about how it worked, and now we want to show that it works this way around. So they have these 2 example problems they applied their networks to, and one is the unpaired video translation, and one is the video super resolution. So what is unpaired video translation? Unpaired video translation means, or UVT, that you have some input sequence of some video, and you would like to translate this, like it says, to another sequence. But it's unpaired because you don't have the same sequence for both of the domains. So in this case, we might have a video of Obama having having a speech and talking to some audience. And we also have videos of Trump talking to of audience. But we probably don't have any videos where they are exactly having the same talk, right?
Seems unlikely.
Seems unlikely, yeah. And that's a data set where it's very hard to cheat on. And so you train the network on using one of these data distributions as your input and try to get the other distributions, so to get Trump saying the same stuff as Obama does. That's unpaired video translation. That's just one example case of unpaired video translation. You could have other examples, like what they did with the TECOGAN was flow fields. So you have some kind of smoke rising, and you want to translate this to other dimensions of video. Yeah, maybe we have a look at this later. And the other task is fairly similar, and many of you already know about video super resolution. So you just give it a low resolution input as here, and you hope that it would provide you with high resolution output. And what we see here is just a single image, but we were talking about video video super resolution all the time. So they have this very nice web page where they provide lots of examples of their outputs of their video. So here we have some video super resolution. And maybe I first show this, and I hope this gets, everyone can see that on YouTube and on Zoom. So I think it's very impressive how this low resolution input gets upsampled and with such a lot of detail. And you don't really have a lot, or not really any temporal artifacts. You might have some spatial artifacts right here, and they show this. So when there is not enough data to sample from the low resolution, you might introduce some mistakes. But even though, I mean, when you're just watching the video, you probably won't even really notice. Here we have some examples of the video translation task, where you have some input domain and try to translate it to some output. Here, the input is Trump. So we want to get Obama to have the same, to say the same as Trump.
So I can't help but notice there's some distortion to the bottom of his face. I think it's because his face just has a different shape than Trump's.
Yeah, I don't think it has something to do with, I think it has to do with some centering the image. So with the pre-processing.
Wait, don't you see like his cheeks are kind of...
I see that, yes, definitely.
distorting a little bit.
Right. Maybe we have another look at the other way around. So if we use Obama as the input and Trump as the output. But it looks really close to real, right? And if we have, they compare their results, sure, to other networks. So maybe here's the input. So if you look at the low resolution input, there are lots of details missing here in these, I don't know what it is, but in these golden parts here. And we have the TECOGAN, and we have other networks they compare that to. And I think, I mean, GT looks
Ground truth, huh?
Yeah. There's not a lot of difference, right? I can't. So yeah. Well, I liked really the one with the gecko as well, because if you look at the ground truth, you can see that the gecko is breathing. If you look at this part, and try to find this in this low resolution image, you can't really. But then look at the TECOGAN, and you can find it in there as well.
Wow.
So all these losses and yeah, the spatio-temporal discriminator they proposed, all these things seem to work.
So what's different between the TECOGAN and all these other networks, which visually at least don't appear that impressive compared to TECOGAN? They're a little blurrier, they're a little choppier. What's different?
I didn't have a really close look at all the other networks. I don't even know if all of them are generated adversarial networks. So the blurry ones might even be other networks.
Fully supervised, no discriminator.
Right, using something like the L2 but I don't know. I didn't really have a look at them. It's just something I assume. I mean, in the paper, they compare their network against networks which are like 10 times as big with 10 times as many parameters. So TECOGAN has about 3 million parameters. And I think they compare it to something with about 20 million parameters, if I have that right. Mm-hmm. And even then, due to their spatio-temporal discriminator and their ping-pong laws, they get visually more pleasing results. They did some user studies as well, which confirms this. And
this is where you pay people on Amazon to click on your stuff and tell you which looks better.
Right. But you don't tell them what's yours before. Yeah, basically right like this. And because the network is so much smaller as well, their processing time is way faster as well. So we're talking about 30 or 40 milliseconds per frame output, while one of the larger networks have up to 1,000 milliseconds, so about 1 second per frame. Yeah. I think that basically puts together what the TECOGAN does and is, right? So first, maybe, are there any questions now from the audience?
We have one from Zoom. Chatterjee asks, regarding optical flow, I have a question to get an idea where the pixel will be at the next instant of time. From a single pixel having pixel intensity matrix, how do we get the vectors attached to each pixel? So if I'm understanding this question, I mean, the first question is, how are we estimating the flow field? And my understanding, correct me if I'm wrong, is we have this flow network F, which takes in a pair of low resolution images,
right,
and outputs the flow field.
Right.
Then we upsample that flow field using bilinear interpolation or something like that. And then we use this high resolution flow field to calculate motion for the high resolution images.
Yeah, that's it.
And so,
as well.
Right. So that's how we go from the intensity matrix, basically the numerical representation of the input images, right? We use the low resolution images to estimate the flow field. And then we use this to transform low or high resolution images as needed by these algorithms. So the warping operation itself seems to be relatively fixed. So given the input image and the flow field, there's a fixed operation which is related to interpolation, sampling the image at non-integer pixel coordinates. But the calculation of the flow field itself is actually learned by a neural network.
Yeah, but only the flow field, not the warping. The warping, like you said,
warping is fixed. Yeah. So hopefully this answers the question. If not, feel free to follow up. It's a good question. There's some considerable literature, and I think something I like a lot about this paper is it gives a good introduction to the field. It gives a fair credit to other papers and really talks about different techniques for estimating flow field, for doing super resolution. And I think the introduction is a great point to start in terms of looking for further reading on this topic.
I think so, yeah.
Some more questions. I think I have some more questions.
Well, I don't know if I can answer them, but
maybe someone in the chat will answer them.
I have one.
Okay.
Can you tell us a little bit about the amount of data that you would need, for instance, to train a network? Well, you mentioned that has several million parameters.
I think okay.
Yeah, how many images would you need from the low resolution and high resolution version just to train the whole thing?
So for the video super resolution, it's quite easy to get paired examples, right? Because you can just downsample any high resolution image or video to get low resolution inputs for your network. And what they did is they went to the site Vimeo and downloaded a whole bunch of videos from there.
Yeah. Okay, but I'm thinking about applications to climate science, in which the amount of data is always limited.
Right.
So how long were these videos? They weren't so long, right? I feel like they were 120 seconds each, and they had maybe some 3,000 frames total. Am I getting that completely wrong?
I have to look.
Let's look. This is great because this is exactly, I think, part of why I want to have this seminar. This isn't just about what a TECOGAN is good for and so on, but this is really about how do we get the relevant information out of these papers. So let's look around for a second and see if we can find it. It'll definitely be in the supplementary information. It'll be about these data sets. We've got temporal metrics, we've got spatio-temporal evaluations. Network.
250 short videos with 120 frames each.
That's really not much data.
Around 3,000 images. Yeah, that's not that much.
So for comparison, how many?
But you double that amount somehow due to your ping-pong loss, right?
That's true.
So it's some kind of video or some data augmentation.
How many total? 200?
3,000 images.
Wait, how many videos?
So 250 videos, each of 120 frames.
It's 20,000 some, right? Frames. 200 times 100 some?
Yes, you're right.
But even so, how many, do you remember, Marcel, how many time points are there in Arrow 5 from 1970 to now, roughly?
I think 350,000.
Yeah. So there's enough data for some of this. But of course, I think I would caution that these videos have 3 color channels. Arrow 5 has whatever, however, depending which version, however many, like some 100 Z levels, and then 10 or 20 different prognostic fields. So you're trying to really do prediction in a much higher dimensional video space. So you might actually need more data for some of this. But of course, I think I would caution that we're having again a feedback loop. What's happening here? 3 color channels.
Maybe someone's trying to ask something via Zoom.
Let's see if we can find the guilty party. Who needs to mute themselves? I think it's me. So you're trying to really do prediction in a much higher dimensional video space.
Okay.
Okay. So you might actually need more data.
Yeah, but thanks for the question. That was really good. I mean, we were talking before about applications on using this as well, right? We were talking about maybe we could use flow estimation just in general more for neural networks in earth sciences, because we have usually these flow estimation fields already in some form due to wind fields, right? This is just some kind of flow estimation.
Well, but actually that's of course a good suggestion, but actually this whole problem has a direct application to climate research. For instance, perhaps you remember the seminar by Christopher Carroll, in which he tried to reconstruct the whole high resolution field of temperatures from sparse observations.
Right.
It's a very similar problem you have said. And actually, I will perhaps send a link in the chat about a paper that we wrote with Freddie Schenk a few years ago, that is also exactly to produce a high resolution output of the forcing for a ocean model based only on sparse observations of one variable. And it is exactly the same problem. It's exactly the same problem as that you have showed. Now, at that time, we tried to solve it with a much, let's say, a poor man's method, based on the analog method. But we had the same type of problems that we have shown here, just to, for instance, the smoothness in time.
Right.
And that was a very important feature for us, because the output of this exercise was forcing fields for an ocean model, so they have to be physically smooth. And we have to solve for that problem in a easier, let's say, more clumsier way. So actually, I'm very happy to have this method here, more refined and more complex, but perhaps more effective.
Yeah,
So,
I was already thinking about another problem like nowcasting or precipitation, because precipitation usually has already some high resolution, but what you sometimes have is that 2 consecutive frames, maybe one frame didn't capture something right, and then you have holes in your rain fields.
Mm-hmm.
So if you use some kind of technique like this, you might be able to reconstruct the missing data as some kind of super resolution, but without upsampling the resolution. Do you get what I'm saying?
I think so.
Yeah, the ultimate application would be, as you said, to use it for prediction, for a real prediction, in which you don't have the information of the high resolution image at time t+1. You don't have it, but you want to produce something that is coherent in time with your previous observation and also a high resolution.
Right.
That if the method would work satisfactorily in that setting, that would be actually, well, wonderful.
Yeah, that would be the holy grail, right? To have some like really high resolution predictions. Yeah.
Yeah, this is something we discussed a little bit before the seminar too, though, is that they don't use these networks for forecasting. They don't just try to learn sequences and then extend sequences. They learn it for translation and super resolution. But there are definitely analogs of these problems.
I mean, of course, that's a setup for climate has a direct application, but the ultimate application would be for real predictions, in which you don't have the whole information for, let's say, to produce the smooth fields, just up to a certain point in time.
Yeah.
So in the climate scenario, what would be the training data?
Well, you could perhaps use. You could test the method first in long climate observations, simulations, sorry, which you have a lot of data to train the networks and test how critical the data volume is.
So this would be for doing super resolution or for doing some kind of parameterization which generates new fields which weren't in the data before?
Well, you could use it for, to achieve a high resolution, for instance, to downscale global simulations to a finer scale of a region, but also for predictions. I mean, you can use to train the network with climate data and then do a knowledge transfer and try to predict unreal observations.
This was a criticism we had, I think, of of this big picture in the big picture episode, I think episode 13. The idea was they were using high resolution observational data sets, and they were trying to learn the downscaling. This is always a point of confusion. It's called the opposite thing in machine learning and earth science, but to learn the resolution increase using these observational data sets and then apply it to climate data, where the climate data really, with some small exceptions of regional modeling, you don't have high resolution data to train on. But the criticism was then, we're now asking this algorithm to generalize to data it's never seen before. And I think, I don't know, it was an issue for the images. I imagine it would be an issue for the videos, but of course, having temporal coherency is definitely a good thing to have if you're going to do that. Yeah.
Well, I think it's worth exploring.
Yeah.
I mean, this method.
There was another question from chat. I think solar energy forecasting using cloud data from satellites might improve for particular locations. Yeah, this is another interest. So if you want a high resolution prediction of where the sun's going to shine, this could be an interesting way of doing it. It's less clear whether you really need temporal coherence in that application. If all you want is the overall power output through the day, but yeah, this kind of combines the super resolution aspects and the idea of working with satellite image data we had from these two previous applications of GANs. And thanks, Eduardo's just shared a link to an article which we will put in the descriptions on YouTube and on our website.
I mean, we have to be careful when using temporal coherence inside earth science applications, right? Because we might not always want them. If we're thinking about a climate model which outputs 2 meter temperatures at a very high resolution, and we have very large time steps in the outputs, there might not be any temporal coherence. So if we use now this restriction of the TECOGAN then we might even introduce larger errors, right? So we cannot just throw it onto everything now and say, yeah, we've got the solution.
That sounds reasonable. Yeah. I want to see if any other questions from chat or anyone else here. I had one more thing I wanted to point out, and we'll wait for any other questions or comments, which is, I mean, this is something we've seen in some form. Again, every paper related to GANs we've seen is that the original idea of GANs is they learn a whole probability distribution such that, you know, the discriminator is telling samples from one distribution from the true distribution from the data versus samples from a generator. And therefore, in order to fool it, you know, the generator can't always output the same value. But it seems in this particular application, there is no randomness. The generator actually always will output the same result for the same input. So it's not going to give you any kind of uncertainty or multiple possible realizations of what the high resolution information might be that you're reconstructing from the low resolution video. It's not necessarily a negative aspect of the algorithm, but it's an important distinction between, you know, how the GANs were originally developed versus how they're being used here.
But in principle, the network is generating a full probability distribution, right? Or
well, never explicitly. It's never really representing probabilities. The discriminator is giving a probability for each of its input that it's real or fake.
okay.
The generator is trying to fool it, but it's never actually generating, for every input it's generating exactly one output. And the discriminator doesn't seem to have a way of detecting this. I mean, there's a big diversity of inputs, so you get a diversity of outputs. But if you gave it the same input twice, it wouldn't give you two different outputs. It may be possible to set up frameworks where this doesn't happen, but this doesn't seem to be the case. It doesn't seem to have been a goal here either.
But then we couldn't use the ping-pong laws anymore, right? Because that really depends on that we have 2 times the same output for the forward and backward direction.
That is absolutely right. We would not be able to use a ping-pong law.
So it is an intention here. It's not something else.
Yeah. Any other comments, questions, criticisms? I think it's an excellent paper. I think we've seen a lot of work from this group. And they're really doing great stuff with fluid dynamics, with computer graphics, with machine learning.
Maybe I should mention at the end, because I didn't do this at the beginning, all the graphics I used, which are not having a source on them, I stole all them from the paper. So definitely have a look at the paper and at the additional resources like the webpage we just had a look on. They have lots of really cool images and videos there.
And I think they have decent source code and good instructions too. So if you have data you want to try this out on, I think it's not too difficult. There's a TensorFlow implementation which you should be able to grab and get going on. Okay, thanks everyone for tuning in on Zoom, for everyone on YouTube for joining. Thank you very much. We'll join back in 2 weeks and we'll let you know about a topic soon. Let us know if you would like to present a paper or present your own work for 5 minutes, or if you have an announcement. Thanks everyone.